Hi, my name is Solomon Culver, and I'm a hospitalist at The Ohio State University. And this is the last of a series of lectures leading up to an analysis of the paper Restrictive or Liberal Transfusion Strategy in Myocardial Infarction by JL Carson. The title of this lecture is Statistical Power and Clinical Trial Design. But before we get started, please go to the bottom of the screen and like and subscribe. So despite all of the complexities and nuances of the design and statistical analysis of clinical trials, it's actually the case that they're fundamentally pretty simple experiments. They're designed to be yes or no experiments. They're not really designed to predict what a given treatment strategy will do for any particular patient, but just to say whether or not there's evidence that a treatment will work. Now, because they are yes or no design and they have the potential of being correct or wrong, there's really only 4 possible outcomes of a clinical trial. They either correctly show a difference between the treatment and the control, they correctly show us that there is no difference, or may do one of those things incorrectly. So the probability that a clinical trial will find a significant treatment effect where there is not actually one to be found is called the type 1 error rate, and it's something that we've discussed in a previous lecture. This type 1 error rate is sometimes written as the letter alpha, and it's what also determines the p-value that we will use to decide to reject the null hypothesis. So just as the type 1 error rate is represented by the letter alpha, the type 2 error rate is represented by the letter beta. And the type 2 error rate, of course, is the probability that the clinical trial will fail to find a difference or a significant treatment effect when one does actually exist. Now, even though we're using this language of type 1 and type 2 error, it's actually a lot more common and a lot easier to understand the converse concept, which is the concept of power. So power, being 1 minus beta, is just the probability that your clinical trial will detect a treatment effect when one actually does exist. Now, as simple as it was to decide on the alpha or the type 1 error rate for a clinical trial, it is far more complex to do the calculations required to set the beta. So this is the equation here on the upper right that describes the relationship between the power, the type 1 error rate, the sample size, and the baseline event rate, and also the minimal treatment effect, the minimal significant treatment effect. And this is a complex relationship. And the way that investigators will usually go about this is they will just choose the alpha, and they will also choose the beta that they want. They will use previous data and experiments to put in the expected control event rate, and then they will decide on the detection limit of the study by choosing the minimally clinically significant effect difference. And once they've chosen all of these things, that the equation here will tell them the sample size required to meet all of those goals. So the power calculation is actually different for every different statistical test or study design. This is an example of a power calculation in survival analysis. And as you can see, it's not simple, and it requires 6 different numbers that the investigators would have to come to the trial having already determined what they would expect these numbers to be. So now, how do we evaluate if a study was underpowered? First of all, if a study is positive, if it shows a difference between the treatment and the control group, then it wasn't underpowered, because the power is really just the probability that your study can detect a difference that's there. Considerations about power really only come into play when the study is negative. And when it's negative, we decide if it was underpowered or not by looking at the confidence interval. So a study, by definition, will be negative if the confidence interval contains the value of zero effect, the null effect value. Now, if that confidence interval also contains effects that would be minimally clinically significant, based on what we specified at the start of the study, then we would say that the trial failed to really distinguish between significant clinical effects and no effect, and that's what we would call underpowered. So to summarize what we've talked about so far, clinical trials are designed to answer one single straightforward question, which is, does the treatment work? Now, that question comes with a possibility of error that the investigators have planned into the study, both a type 1 and a type 2 error. The investigators can easily select the type 1 error, but the type 2 error, or its converse, the power, require a lot of assumptions and estimates that they would have to come into the study having already made. We know that a study is underpowered when it's, first of all, negative, and second of all, the confidence interval must contain some point that would meet the minimum significant clinical effect. So again, we come to the MINT trial, which was a clinical trial designed to determine if increasing the transfusion goal to a hemoglobin of 10 would improve outcomes in acute MI as compared to the current transfusion goal of 7 to 8. The authors used data regarding the outcomes that we're having right now at our current transfusion goal, which is the control event rate, and they used the value 16.4% in their sample size power calculator that we showed on the previous slide. They also chose an alpha of 0.05, a beta of 0.2, and they determined that the minimal clinically significant difference would be 20% difference between groups. So the authors decided that a 20% difference in mortality or reinfarction rate would meet the minimal clinically significant threshold. And we can see here the outcomes data for the study, and the primary outcome had a point estimate of 1.16 and a 95% confidence interval that ranged from 1.0 to 1.35. So this is a negative study because that confidence interval contains the point of no effect. Therefore, in order to determine whether it was underpowered, we have to see if that confidence interval also contains the minimal clinically significant effect, which they decided would be 1.2, and it does. So by that criteria, the primary outcome, or the study was underpowered with respect to the primary outcome. And they also have secondary and tertiary outcomes, none of which were properly pre-specified or corrected for multiplicity, but we can also see that by the criterion that we used, the study was underpowered to detect the appropriate effect in any of these outcomes.